Good afternoon, everyone. Here's an elevator problem that's similar to the last elevator challenge problem, except this one involves an inequality, and it also shows us that we can get information about an elevator from what's happening with the person inside of it. So that's some interesting, neat stuff going on there. Let's begin with the problem description. We are designing an elevator for a hospital. We're told that the force exerted on a passenger by the floor of the elevator is not to exceed 1.60 times the passenger's weight. The elevator accelerates upward with a constant acceleration for a distance of 3.0 meters, and then it starts to slow down. And we need to figure out what is the maximum speed of the elevator. And now there's no intricate setup that's required here before we jump into the free body diagram or Newton's second law. There's no calculus in this one, but this one is an interesting problem because notice we're given information about the passenger and how the floor exerts a force on them, and we're supposed to use that to figure out how fast the elevator is going. So that's a little weird. You wouldn't expect to be able to use that information to answer that kind of a problem, but you can. It's kind of cool, and we'll figure out here why that is the case. So let's jump into the free body diagram of us inside of the elevator. And if we're standing in an elevator, there's really only two forces that we have to account for, and that's our weight that pushes down on the floor of the elevator, so that's the W vector there. And then there's the normal force of the floor pushing back on us. And we were told that the normal force can't exceed 1.60 times the weight. But in the most extreme case, it is allowed that the normal force could be equal to 1.60 times the weight. And so that means that in the most extreme case, with the biggest acceleration, which would mean the largest velocity for the elevator, the normal force, or the normal vector, pardon me, this blue one, is going to be 1.60 times the length of the weight vector here. Let's also remember to account for our acceleration as the elevator moves upward, as shown by this dotted red vector here off to the side, and that's it. We don't have anything else to draw here. Let's move the diagram aside and start summing forces in the x and y direction. Speaking of the x direction, we'll kick things off there because it's super easy. We're not moving to the side as we stand in the elevator. We're standing still, and the elevator is bringing us up in the plus y direction. So the sum of forces in the x direction is going to be 0. Very simple. For the y direction, we have the normal force minus the weight is equal to our mass times our acceleration as we move upwards in the elevator. And here is a reminder about the inequality that I mentioned before. We were told that the normal force can't exceed 1.60 times the passenger's weight. And so if you want to write that mathematically, it would be like this. The normal force is less than or equal to that value. And we said in the most extreme case, which would give us the largest acceleration and hence the largest maximum speed of the elevator, we would say, hey, the normal force is equal to that value. So let's say n is equal to 1.60 times w and plug that in to the next line here. The next step would be to factor out our weight, w, from both of these terms on the left here. So as you can see, we're taking our weight times this difference, which is maximized by choosing 1.60. Okay? So we're still working within the confines of the problem description, but we've chosen the largest value that the normal force could be. And so if you take this difference here, that's very simple. 0.6 times our weight is equal to this. let's rewrite our weight as mg, because notice there's a factor of mass on both sides, our mass, that we can eliminate. And this tells us the acceleration that we are experiencing inside the elevator as a result of the limitation of the elevator's design, we experience 0.6 times the acceleration due to gravity. And the key to using this information to figuring out the maximum speed of the elevator is that the elevator has this same acceleration as well. And so let's take this value and plug it into a kinematic formula for the elevator itself. Specifically, this one here. Right? So we want the final velocity in the y direction of the elevator. And we need to figure out what we're going to plug in over here, as well as take a square root of both sides. So let's start off with the first term here. We are not told about any initial velocity in the y direction when it comes to the elevator. We are not trying to step onto this elevator as it's moving upward. So we are going to set that term equal to 0, which means we only have this chunk to deal with. We can apply the square root of both sides, like I mentioned before, which will give us this in the next line. So we have the final velocity in the y direction of the elevator isolated, and all we have to do is plug in the values that we solved for and the ones that we were given. So the acceleration in the y direction is the same as us inside of it. That's the value that we solved for before. That's that 0.6 times g. And then the delta y is the displacement that the elevator undergoes when it has that acceleration. That's the 3.0 meters. So plugging everything in here, that's what we get in this line. And my calculator gives the following number as the answer. Now, remember, we have to deal with significant figures. And in the problem description, we were given a number with 3 significant figures, the 1.60, and then one with 2 significant figures, the 3.0 meter value here. And we have to answer our final number, or our final answer here to the smallest number of significant figures from the problem description. So if we truncate that right here, 3 is smaller than 5, so we ignore everything to the right of the 9 here, and our final answer, finally, is 5.9 meters per second. The maximum speed of the elevator, 5.9 meters per second, comes from our restriction that we put on how the normal force acts on the passenger. Very interesting stuff. And that's it for this problem. Thanks for watching.